Okay, hey everybody. So in this video, I want to continue our conversation about polar coordinates as a alternative coordinate system to Cartesian coordinates. So we've been discussing these. In our last video, we derived a way to translate between the two coordinate systems. So given an x and a y, here's how we could compute the r and theta. Given an r and theta, here's how we could compute the x and y. And I should maybe say at first, there is a little bit of ambiguity here, right? Some of which we discussed last time. So we saw that this formula doesn't work always. We sometimes have to add a plus pi if our point is in the second or third quadrant. On top of that, I just want to point out something that I did not say last video is you have to be wary of what might happen if your x value is equal to 0. If our x value is equal to 0, that would mean that the point in question is lying on our y-axis. And that would mean that our angle is either pi over 2 or 3 pi over 2, depending. Right? Of course, this formula would give us an undefined expression, so we would just have to use our common sense and our knowledge about where the point is, namely that it's on that y-axis, to figure out what our theta would be in that case. Those two examples of our theta value being sort of finicky, right, sort of that undefined expression and then the possible plus pi, are two examples of sort of the finicky nature of polar coordinates. In short, polar coordinates can be a little bit more finicky than Cartesian coordinates. There are some ambiguities or some non-uniqueness expressions that can potentially pop up. And there are three of them that I wanted to point out. So some examples of non-uniqueness here. The first one is simply, the fact that we all know and love, which is that our measurements of angles typically are 2 pi periodic, in the sense that if I had a xy plane, let me go ahead and draw one here. If I have an xy plane and I want to measure a certain angle, let's say this angle right here, right? So if I wanted to measure an angle, I could measure this angle, and I could get a value, maybe that's pi over 4 or something similar. But I can also equivalently think of this as the angle of what I would get if I went all the way around the circle and then ended up back there, right? So on the one hand, I could think of it as maybe pi over 4. On the other hand, I could think of it as 9 pi over 4, in which I've gone all the way around the circle. That's 2 pi, angle measurement plus an additional pi over 4. So, right, our sine and cosine and our trig functions automatically reflect this because they are 2 pi periodic, right? Meaning that you would get the same expression if you plugged in cosine of theta, or you plugged in cosine of 2 pi plus theta. And more broadly, it's not just limited to 2 pi, of course. This could become 4 pi or 6 pi or 8 pi. So it's really theta should be the same thing as theta plus 2 pi times any integer k, right? So 2 pi, 4 pi, 6 pi, 8 pi, etc. That means that there's the potential of describing the same point in two different manners, right, in polar coordinates. So we could say, for example, that the point where r equal, and this is in polar coordinates, so it's an r and a theta, so the point square root of 2 comma pi over 4, right, which is the point we explored in our earlier video. That's just the point whose Cartesian coordinates are 1 comma 1. I can describe that as root 2 comma pi over 4, but I can also describe it as root 2 comma 9 pi over 4. And it would be the exact same point that I'm describing. So in Cartesian coordinates, if I have a point x comma y, the x-coordinate and the y-coordinate uniquely determine or uniquely describe the point that I'm looking at. In polar coordinates, that is not the case, right? We can see here that I have two different representations in polar coordinates of the same point in space. So that is a potential ambiguity of the polar coordinate system. Additionally, we can, as I'll say, there are two other bullet points that are worth discussing. Number one, the origin, right? The origin in XY space, it's nice, it's unambiguous in Cartesian coordinates, it's just the point 0, 0. In polar coordinates, it's a little bit weirder, right? This point is the point where r is equal to 0, that's true. But because r is equal to 0, the measurement of theta doesn't really have any meaning, right? So because r is 0, theta could really be anything here, and I would still be describing the point 0, 0. We can see this explicitly in our formula down here. Notice that if r is equal to 0, if that distance from the origin is equal to 0, then theta could really be anything, and I would still get x equals 0 and y equals 0. So there is an ambiguity in how we describe the origin, or a non-uniqueness in how we describe the origin. R equals 0, theta could really be anything, and any of those pairings, r comma theta, would be describing the origin. Finally, we have to consider what might happen if we plug in a negative r value. And so for this one, I'm going to try to look at a specific expression here. Let's talk about the point, right? This is maybe our favorite point. Let's talk about the point where r is equal to square root of 2 and theta is equal to pi over 4. I guess because we're talking about negative r values, let's let r equal negative square root of 2. So if it were a positive square root of 2, right? So if it were a positive square root of 2, we would extend our drawing out pi over 2 unit. I'm sorry, if it was a positive, I think I said pi over 2. If this is a positive square root of 2, I would extend my r value out square root of 2 units, and then I would measure up from the x-axis in the direction, in this sort of counterclockwise direction, pi over 4 units, right? And so this is the point that would correspond to positive square root of 2 pi over 4. In order to introduce the negative sign, what I'm going to do is I'm going to flip this picture across the x-axis, across the origin. And there's good reason to think about it this way, right? I could think about getting to this point by going up pi over 4 units in terms of angle measurement, and then extending myself out root 2 units of distance. So if I wanted to go negative root 2 units, I could just go in that negative direction here. And so this point down here would correspond to the point negative root 2 comma pi over 4. Okay, so if we have a negative r value, we could proceed as if we were going towards our positive r value, computing that positive r value, and then we would end up flipping it across the origin to get the negative r value. In other words, this point right here is equal to the point, grabbing my pen back, so this is equal to the point that corresponds to a positive root 2 and then a pi over 4 plus pi, right? And if we see that, we can get to this point using two different strategies, right? I can either go up pi over 4 units and then go in the negative direction, root 2 units, or I can think of it as going all the way around pi over 4 plus pi units. And maybe I'll highlight that in, let's say, a purple color, right? So the pi over 4 plus pi, that would correspond to going all the way around here for my theta, and then extending from the origin out root 2 units. So this is an additional ambiguity. And in general, if I have a negative r value, right? So if I have an expression, let's say it looks like negative r comma theta, that is equivalent to the expression r comma theta plus pi. Right, so the takeaway message here is that there are several different ways that we can describe a single point in polar coordinates, and we did not have that ambiguity in Cartesian coordinates. We can consolidate this, or we can work through this using the following schematic. Here we go, the following schematic, right? So ways that we can get around this non-uniqueness. If we want to be able to describe a point unambiguously and uniquely, we can still do that using polar coordinates as long as we restrict what our possible r values and theta values can be, and as long as we're not talking about the origin. So every point in the plane except the origin can be written using a unique pair of polar coordinates. So if we want to get at this uniqueness, unique pair of polar coordinates r comma theta, as long as we specify that r is positive and theta is between 0 and 2 pi, right? We can allow for points to be written in these other representations, so letting the r value be negative, letting our theta value be something like 6 pi, whatever, everything that we discussed earlier. So we can still describe points those ways. However, we recognize that we could translate the points to this standard form if asked to. Standard form meaning r is positive, theta is between 0 and 2 pi. And that this standard form gives a unique representation of the point. This does not work for the origin, but it works for all other points in the plane. For the origin, we do not have uniqueness of theta, but identifying r equals 0 is enough. Once we know r equals 0, we know that we are looking at the origin. So that is how we get a little bit around this non-uniqueness issue. And that allows us to continue discussing polar coordinates with in a given standard form. So that's all I've got for this video. Yeah, thanks so much for watching.